This sequence will look at an extremely important application area of resistor capacitor circuits. This has to do with the property of capacitors that enables them to store charge, that enables them to be able to remember state, okay, to remember stuff. And by doing so, we're able to create the foundations of memory systems. Okay, I'll show you today how by storing charge on capacitors, you can build memory such as DRAM or dynamic RAM and SRAM or static RAM, caches and things like that that you will learn about in future courses. These form the foundations of all of the memory that you see in your laptops and other handhelds and other devices. The key to all of this is the ability of the capacitor to store some state on it for a extended period of time. So in today's sequence, we're going to look at state and memory and how we can construct a memory element using our capacitor. Before we begin, let me do a review of what you've seen so far. We will use some of these principles in what we cover today as well. So far you've seen many examples of first order circuits. You've seen RC circuits, you've seen resistive inductive circuits, and so on. Okay, a canonic RC circuit that you've seen is the series RC circuit with a voltage source in series with a resistance and capacitance. Now, we also said that in the examples we worked out, the capacitor had some voltage Vc of 0 across it. So if we cared about what happened to the voltage Vc after time t equals 0, we said let's start off with an initial condition Vc of 0 at time t equal to 0. And in the examples we did, I also told you that the input t, Vi of t, was equal to some DC value for t greater than or equal to 0. Okay, we said, let's not worry about what happens to Vi before time t, and let's just know that it is Vi for time t greater than or equal to 0. Okay, today we're going to see why is it that we were able to make that assumption. Okay, why is it that we did not really care about the value of Vi before time t equal to 0. Okay, we'll see the foundations of that today. So for a circuit like this, we went ahead and did the analysis, and we saw our canonic expression for the capacitor voltage Vc, and that was given by Vi plus the initial condition on the capacitor Vc of 0 minus Vi, and that times e raised to minus t over Rc, where Rc was the time constant. Okay? So this was a canonic equation that governed how an RC circuit like this behaved. I also want to remind you the reading for all of this stuff is section 10.3 of the textbook. We also covered an intuitive method of analyzing RC circuits. Let me review that very quickly. I personally find that intuitive approach to be one that I keep coming back to and using all the time. So let me share that with you again. So here's my time axis, and here's Vc. This is 0. And so we said that for a capacitor, let's say we started off with some initial value on the capacitor. Clearly the initial value is always going to be, at time t equal to 0, was going to be the initial value on the capacitor. So in this case it was Vc of 0. We were given that value. Now given that value, there were two forms in which the capacitor behaved. One was a form that went like this, and second was a form that went like this. The form that went up was characterized by the equation 1 minus e to the minus t over Rc, and the decaying form was given by e to the minus t over Rc. Okay, so let's look at both of these forms. So we started off with Vc of 0. So for the one form, if the input voltage Vi was greater than the initial condition on the capacitor, then we knew that the final value on the capacitor was going to be Vi, and so it would be the rising form. Okay, intuitively this rising form was governed by the following equation. Recall I said this was the form e to the minus t over Rc, so I write that down there. And then we said let's take this difference, okay, and that is the difference over which the capacitive voltage is going to increase. So that difference is a Vi minus, let me just call this V of 0 just for convenience. Okay, so let me call that V of 0 for convenience, and a bit of a shorthand notation. So that is V of 0, the initial condition on the capacitor. So this part of the equation here, this piece here, reflects this curve starting from this offset. Okay, so let me go ahead and add the offset to it. So it's V0. So V0, which is Vc of 0, times Vi minus V naught times 1 minus e raised to minus t over Rc governs the rising waveform. Now, if Vi had tended to be lower than a Vc of 0, let's say Vi was down here, in other words, if the input voltage was lower than the capacitor voltage, then at the end of the day, the capacitor would end up being at Vi. And in that case, I would have a decaying waveform. Okay, of course, the time constant of this would be Rc. Okay, so the time constant would be Rc in both cases. And what I would see, the equation for the decaying form is given by a similar expression. Notice that the form is e to the minus t over Rc. And notice that the value that decays is V naught minus Vi. So let me write that down. The V naught minus Vi. So let me write that down. And then there's an offset of Vi, so I add up the offset here. Okay, it's pretty straightforward. Okay, I look at the difference over which the waveform rises and pick one of the two forms, either decaying form or the increasing form, and then add to that the basic offset. Okay, those are the two intuitive forms that we looked at. Okay, we will go back to those again and again during this sequence. And as I said before, the upper one is characterized by a rising little form like that, and the lower one by a decaying form like so. Okay, so that's it for the review. Let's dive into understanding the memory property of capacitors in greater detail.